Good morning, everyone. It's my pleasure to welcome here Professor Michael Stingl from TU Erlangen. And his talk is about continuum stochastic gradients for spatial optimization. So let's hear what he says, and I'm really looking forward to this.
Thank you, Marek, for the kind introduction. I guess you should probably start the talk. I don't know how to. Yeah, as Marek said, this is about design optimization via the continuous stochastic gradient.
I'm sorry that I interrupt you, but we couldn't see the presentation.
Sorry. Is it okay?
Yeah, it's better. Thank you very much.
Thanks, Marek. Sorry.
Okay, so I'll try again. And this is joint work with Lukas Pflug and Adrian Uhlein. Both are from my group in Erlangen. Lukas is a senior researcher there since many years, and Adrian is quite a fresh postdoc now, and he has done most of the contributions here. So I'm happy to be here. And please, whenever there's a question, just interrupt and ask. I think this is better because I have quite many slides, so it's better to ask immediately. You have a question. Okay, so actually, the class of problems we consider, it's not only like topology or material optimization. You could think of PDE constraint optimization in general. And today, everything I present is already finite dimensional. If you think, for instance, of an elasticity problem, then it would be already discretized by the finite element method. So we start from an equation like this, which is our state equation, and y would be the discretized state variable, finite dimensional. And then, as we want to solve a design or a control problem, there needs to be some control. We would most of the time denote this control by u. Later, then when we talk about topology, we use a pseudo density, then it will be rho. I already apologize for this. And then there is another vector I call x, and this is simply data. Now, every equation, it depends on additional data, and also control is data, but the difference between u and x is that u we can control, and x we cannot. Then we have some structural assumptions. For instance, we say that simple constraints, control constraints like box constraints, we treat more or less directly, but we need a convexity assumption of those. As I said, x is our uncertainty vector, and there's another kind of strong assumption for which sometimes you need a regularization strategy. And that is that this guy here, that's the equation for any choice of the control, admissible choice of the control, and for any choice of the data should admit a unique solution. And the reason is if it admits a unique solution, then we can introduce something like a solution operator, which would assign any choice of control and data a corresponding solution of the state equation. Well, and this allows us to write optimization problems in the so-called reduced form, which is here. So we can define an objective or a constraint as a function of control and data only by using another function which depends on the control and on the state. But in that argument, which depends on the state, we simply insert the solution operator, right? So this is what you typically do as reduced form. Now, having this, so this is our general framework. So it's discretized finite dimensional, but otherwise, as you can see, are very general. We can define different types of optimization problems. And so let's for a moment only assume that we fix these additional data from that ZX. And then we get something we call a nominal problem, a reference problem, which is not subject to uncertainties. And then we consider two different types of problems. Either we just minimize a cost function over that rather simple set, capital U, which is our control or design set, or we have an objective which does not depend on this additional data, and the additional data, they appear in a constraint. Let me say that this is something you typically do, that there is no X dependency in the cost, but this is not a restriction of generality, because you can always move the objective to the constraints by introducing an additional variable. So this is really just to simplify notation a bit. Yeah, and another thing we can immediately observe due to this definition of the little j here, which was a function of control and state, typically such functions, they are never convex because you have to involve these say design to state operator. And even if that has a simple structure, typically you lose, in general, you lose convexity by that. So we are dealing with continuous, nonlinear, non-convex optimization problems. And as the evaluation of J for a given U and X requires to solve a state problem, it's typically expensive because if you think about the 3D elasticity problem, we need to do discretization and we need many elements. So every evaluation costs significantly something. Okay, and this is now part of the issue. If you now would like to consider not only one choice of data, but say infinitely many choices of data, and you look at them as uncertain data, this is, as I said, because we cannot control them. And I would start to compare 3 different ways how we can model these uncertainties in an optimization problem. The first one, maybe the most well-known formulation, is the so-called robust optimization model. In this robust optimization model, you have you try to do an unbiased protection against all realizations of uncertainties. Unbiased in that sense means that there is no weighting. All the scenarios, as we call them, are equally important. And what you obviously have here, at least if X is a continuous set, is like a semi-infinite optimization problem because you're getting infinitely many constraints. Okay? But then there are alternatives. For instance, you could the uncertainties that could enter. You could have something like a probability density, or you could look at X as modeling a random variable. And for this talk, the assumption is always that this goes along with a probability density mu, and then you could handle these uncertainties by minimizing, instead of the nominal property, an expected property. And how do you compute this expectation? To compute the expectation, you have to integrate your little j, which is your cost, your compliance, whatever, depending on the problem you solve, over this uncertainty set here, and you use the weighting, which is given by your probability density mu. Of course, you can do that only in practice if you have access to such a probability density. That can mean that you know the full density from the beginning, or there's also variants in which you simply need something like a sampling or an oracle, right? So you cannot write down by paper and pencil the particular form of this probability density, but still you have a computer code, and it would follow the probability density to sample uncertain realizations of the uncertainty for you. So in both cases, this can make sense. And actually, we will not only look at these simple problems here with kind of a linear expectation of J, we will also look at more complicated structures where this undergoes another nonlinear transformation and then even nested expectations. And I will also show you an example for this, that you have 2 different types of uncertainties here, X and Z, and then you just have to integrate once, you undergo a nonlinear transformation, you integrate twice, and you can even have another nonlinear transformation, and so on and so forth. So such problems exist even in design optimization, as you will see. And then there's a third type, the last type we can read, and this is the so-called chance constraint. For instance, in topology optimization, you know that also as reliability topology, right? Reliability-based topology optimization, because there, what you try to do is you try to restrict the failure probability. I wrote it here in the opposite way. So there is some probability level P, which can be 90%. And what I try to compute with the chance constraint is the probability of being successful. But obviously, probability of success and probability of failure is just one minus the other. You know? And how do we compute such a chance constraint? Here, you need something in addition to that. You need a characteristic function. And you see the original constraint is here. So whenever this is smaller or equal than 0, this expression, which means that our original constraint is satisfied, we would count a 1 here. And if it's infeasible, we would count 0 here, and then we integrate these ones by the probability density mu here, and yeah, this is what it is. So you get kind of the probability of success for your function. Again, an integration is involved. Now, I just want to come up with a first example of a topology optimization problem, which I would like to use to compare these 3 different types of concepts to include uncertainties in your problem. And later, we will then talk about an optimization algorithm, which can be more or less all of them. Okay, so the problem, I guess that everybody knows a little bit the story about density-based topology optimization, so I try to keep it short. So this is our design domain, where we have some fixed material in this gray area. The yellow one is the design area. Here we have homogeneous Dirichlet boundary conditions, and we model what we want to decide, where to put strong material, where to put no material actually, but we use the typical regularization, replacing void by a weak material. So this is an interpolation using Simplon to enforce black and white solution. And this is our density variable, which is accordingly between 0 and 1. And we have a volume constraint, which limits the amount of material used for the strong material. And what is special about this problem is now that we have infinitely many loads. This is the profile of only one load. So you can parameterize the load by a rotating angle, right? So for one angle, the load profile would look like this, but we assume that we have infinitely many of these loads. And now, in the beginning, I said we would look at discretized problems. So with some methods, say finite elements using triangular elements, you discretize your problem, and then you see here the counterpart of our density variable, and this is the discretized state equation with the stiffness matrix here, depending on our control or design, which is our pseudo density variable. That's the solution vector, and this is this right-hand side, which is parameterized by this direction or angle of the angle at which the load attacks. So we have infinitely many state problems, and for each choice of the, say, uncertainty alpha, this certain uncertain angle, we get a different solution via alpha, and this way we can write down the solution operator. Just formally, we still have to solve that equation to evaluate the solution operator, of course. And then what we do, we minimize here the compliance, which is just the stiffness somehow in the direction of the load. So you, in the finite dimensional setting, you have this inner product of the load vector with the corresponding displacement, okay? Giving you the stiffness deformation at the boundary for this particular load. So this would be the choice for one alpha. And now this is just to say that we also use some regularization, so filter techniques, but the emphasis is not on that. So I don't show the details here, but if you're interested, I can explain. And now we compare these 3 different types of optimization problems. So we don't do optimization yet. We just evaluate the different constraints and see which bound we can choose here for a given design. So imagine that this would be a solution. I can tell you it's already quite a good one. So black means that we have the strong material there, and white means that we have the weak material here. And what we do now, we evaluate our compliance for this design in every direction alpha. And the way we visualize that is simply that the value of the compliance is proportional to the length of this ray here for a given angle alpha. It means for a load coming from here, the structure is a little bit stiffer than for a load coming from here. And also we have for this design a lot of symmetry. And now we can say, okay, if we look at the robust problem, which is here with the infinitely many constraints, we need to protect against all uncertainties. That means that the bound for which our design is feasible is indeed the maximum of our all design. So it would correspond to this outer circle here. If we go for the expectation, so now we put the expectation into the constraint to make it a little bit more comparable. What is it? I mean, it depends on the probability you have, or on the probability density function you have. But if you have equal probability for all cases, this is what we assume here. It's just the average, right? Which would be the green line. And now, if you go to the chance constraint, so what is that? So we have to be feasible for, say, 75 or 95% of all cases. We are allowed, so we can express it in terms of failure probability. For this, we are allowed to cut off like 25% of that surface, and for 95%, we have failure probability 5. We are allowed to cut off only 5. So you see, if we increase the probability level in the chance constraint, we more and more approximate somehow the behavior we have for the robust constraint. And this is something I would like to also advertise, that if you have a good solver for this chance constraint problem, which probably most of the times is assumed to be the hardest one to solve, but if you have a good solver for this, it also kind of covers, at least in the limit, the robust problem also. We will also later see that in the example. Okay, now a last thing to this little example is that, of course, what you get here depends heavily on both the design, but also on the probability distribution you assume. So if, for instance, if you take a different design, still looks like a reasonable design, and I plot now the blue line here, which corresponds to the angular compliance here, you see I can only see the compliance values here at the angles where we have these struts in the design. So if I want to see the full picture, I would have to rescale. And now my design is here. So you see how much worse the answer of that design here is compared to this, right? And then a consequence of this is that now the different models will give you completely different answers, right? So you can see that the robust is out there while the expectation is in here. So there's a much larger difference compared to this. But still what you see is with the high probability chance constraint, you go still, even for that, quite close to the robust case. Okay, and then, of course, I said also the information about the distribution is important, because you may also be interested in a distribution like this, that you have like still infinitely many loads, but you know that somehow some loads are prioritized. So you could have a Gaussian distribution like this, and of course then the performance of that structure would be already much better. So this is something, so it's a modeling question, right? How you want to your uncertainties to enter the problem. Okay, so this is only very short word about the case of finitely managed scenarios. And the message is essentially if the scenario space X consists only of finitely managed scenarios, there's actually no debate about designing a new optimization solver, because then, as you can immediately see, that the robust problem turns into a standard NLP. I just may have many constraints, but this can be handled. For the expectation, I have this discretization here, so it looks like a weighted multi-load case. Also, this can be handled for tens of years efficiently. And a little bit more complicated is the chance constraint. You also, here the integral is turned into a sum, and you have these weighted nonlinear functions. But if you add a little bit of smoothing for the characteristic function, turning it from a discontinuous function to something which you can even differentiate, you get also, say, a sequence of NLPs by which you can approach this. So here the interesting thing is actually to focus on continuous uncertainty sets, which is much harder. And I will focus on the stochastic problems, so problem number 2 and 3, but we don't forget that we can at least approximately cover the robust case as a limit of the one with the chance constraint. So what can we do, or what do people do in literature? How do they approach such problems? Probably the most prominent solution strategy is to go for an a priori discretization. You have integrals in all the problem formulations, so you suggest to use a quadrature rule with a priori chosen weights and supports. But the problem is you have to close these supports at which you integrate, right? Your integration points, in other words, you have to choose them for all admissible designs, because you don't know what the optimal design is in the beginning. And this is a kind of a difficulty. So it typically works only for a small dimension of the uncertainty space. And there's also a problem with the resolution that's related to the fact that you do not know the optimal control. And here's a simple example from one of our papers. It's actually constructed, academic, but there are examples in problems where we try to optimize the color of a particular product. I will have that example later. Here we see the same phenomenon. And the idea is as follows: you don't have to read the analytical formula here, but what you have is you have a one-dimensional control, which is U, and you have a one-dimensional uncertainty, which is X. And now if you look at your expectation, what you would do, you simply analytically solve this integral, and then you have a closed expression for U. And that closed expression for U, it's a convex function between minus 0.5 and 0.5. So it has only one minimizer. This is your global minimizer, and you can easily solve that problem. Now, if you start to do an equidistant discretization of this guy, so taking your quadrature point, and now you may say, okay, equidistant, there are much better choices, but the issue is you don't know. So your function is also parameterized by the control, by the U. So there's not much better you can do as choosing equidistant points, because you don't know at the end where the mass of your distribution is, because it depends on you. Okay, so if you do that, for instance, with 4 points, your function looks like this. This is your approximation. If you do it with 8, it's a yellow curve. If you do it with 16, it's that curve. And what you see, the more discretization or the more integration points you take, the better is your approximation, but also the more additional local minima you introduce, which are completely spurious and artificial. Now, if you take a nonlinear solver, you might simply end up here, and that's it. You cannot do anything about it. So there's always this question of, how do I a priori choose my discretization with this approach? And this is an issue. Okay, the second one is, you can say, okay, that's fine. So I simply use Monte Carlo or fuzzy Monte Carlo. This is the probably the most prominent tool for higher dimensional integration. But that would mean that whenever you do a function value evaluation, and maybe try to do gradient information in your optimal control problem, you have to do an almost exact integration, meaning you have to solve thousands of times your state equation just for getting one function value. And then, even if you have this, the question is, how can you go get somehow differentiability information? Because you always have kind of an inexactness in your evaluation, and it's hard to quantify it. So there may be solutions, but you see it's also not so easy. And then the third way, and this is also what people try to do in topology optimization since approximately, I would say, 5 to 10 years. They use the famous stochastic gradient type methods, which have actually been invented already more than 70 years ago, but now due to AI and data science, they have this new revival, and they are very prominently used. So people use them also for structural optimization, but the problem with them is they heavily rely on the fact that you need an unbiased estimator of your gradient. So what they do essentially, not like in Monte Carlo, where you would in every iteration, you would have to do almost exact integration. They would take just one realization of the scenario in every iteration, right? Just at random. And then you repeat that, and still you can show that in expectation you get kind of convergence for this problem, but it's not like a monotonous method. It would be oscillating, and everything would be a little bit weaker, the notion of convergence and everything. But the problem with that is you need this unbiased estimator of a gradient. So if we look, for instance, at our chance constraint problem, and we would treat the chance constraint by a penalty or an augmented Lagrangian approach, there would be already, so here's the linear structure of the integration. This is our integrand, so this would still be okay, but then there's already outside this is a nonlinear transformation, which I need to penalize, and this is already something which you cannot put into SG anymore. So it's simply not compatible. And another thing is these nested structures, and here is my example, and I will also show results later. So this is also structural optimization, but now it's not for elasticity, it's for like optical properties. The idea is somehow to design the color for such an unorganic pigment. This is a very well-known bridge, and it has this nasty, or maybe some people would say nice red. And that comes from hematite, and hematite is a so-called organic pigment. And now, believe it or not, it's possible to control the color, the appearance of the color by controlling the shape of the particles. But of course, you have millions and millions of such particles, right? And it's not like so the reactor in which this color is produced, it's like 10 meters high. So you can imagine how many particles you have in that. So it's not like printing something like in elasticity. So you have much more coarse possibility to control. But still, with mathematics, you can check how would an optimal shape, for instance, of a particle look like to drive the color in a certain direction. This brings up the question, how do we measure color? And there are many metrics for measuring color. Typically in science, the so-called LAB coordinates are used because people say it's kind of if the distance of two colors is large in that LAB ball, then you would also, as a human being, you would also receive it as large. And if two points are close together, you would always also say, okay, this is right and this is right, I cannot distinguish it, right? So this is the reason. It's somehow rescale. Okay, and what is the problem here? The problem is how to compute this color. For this, we have to solve a state problem also. It's about electromagnetics. It's in 3D. So we have to solve 3D Maxwell's equation. And as these colors need to compute a so-called reflectance spectrum, you have to do this in the time harmonic setting. And that means you have to solve your problem for any choice of the wavelengths in the visible light. That means from 400 to 700 nanometers. So this is the first thing, your first integration variable. And the second thing is that as you have millions and millions of particles here, if they have an anisotropic shape, you have no control about their over their orientation. So if light is coming from here and the observer is standing here, what would he or she see? Simply a mixture, an expected appearance of all the different orientations. So now in the 3D space, you need two variables to parameterize an arbitrary orientation. So we have already a three-dimensional integration, one for the wavelengths and one for the orientation. And if I show you the whole diagram of how we go from a given design of a particle, so this is now with finite elements, right? We somehow discretize the particle. We have two different materials here. To the color, you have to go all this way. You essentially have to solve 3D Maxwell's equation for any choice of wavelengths from 400 to 700 and for any orientation in space. So infinitely many scenarios, but even in a three-dimensional space. It's a little bit more than before. Once you have this, you can compute some quantities like absorption and scattering. And then first you have to compute the expectation with respect to all the orientations. So this involves a two-dimensional integration. Then you need to undergo a nonlinear mapping, which does something like homogenization. So it gives you the answer. So you go from the properties of an individual particle to a thin film, a little bit like homogenization, but simpler mapping. You can look it up under that name, Kubai-Kamung type mapping. And then you need to go to the color. And the color is again a weighted integration with so-called color matching function over the wavelengths. So this is your third integration. And then you have the so-called X, Y, Z coordinates of color. And they can be transferred into the LAP coordinates, doing another nonlinear mapping. So you really have this nesting of nonlinear functions and expectations, if you want to read it like this, as I suggested before. This is what your model is. And so SG would never fit for this. Okay. So that's why, that problem was the main motivation why we invented a new method. And this is the continuous stochastic gradient method. And it's actually like, it's sort of a compromise between a stochastic gradient method and the standard, the deterministic gradient method, because what it does a stochastic approximation of function value and gradient, and the key is that this is getting better and better over the iteration. This is already the whole idea. I will detail it, but not much more. In order that you can do that, it requires some additional regularity, and that is that the answer of your system, if we go back to the elasticity example, it does not vary spontaneously if we change our uncertainty. So you need some regularity, not only with respect to the choice of your design, but also, for instance, in this example, with respect to the direction of your node. But this is very often given in such problems. And also you cannot treat chance constraint with characteristic functions directly. We need also here to rely on the regularizations as the one we have seen already before. That method works for large N, which is our design space, which is important because we want to go for maybe millions of design elements. And it works for reasonably sized D. And this you always have to keep in mind what high dimensional integration means. So even with Monte Carlo, you cannot go beyond 20 or 30, getting a reasonable precision for evaluating an integral, right? So this is also our limit here, but we typically work with 2, 3, 4, as you have seen in our examples. And another nice thing, so the idea of the method is essentially how to approximate function values and their gradients. And that's why you are not forced to use simple steepest descent idea. You can also combine with more advanced sequential programming techniques like SQP, and in particular in topology optimization, this method of moving asymptotes is very prominent. So you can also combine this idea with that one. This is also what I will do in the remainder of the talk. Okay, so to be more precise, I would like to explain the idea now, and I go back to this simple function, but this is just for demonstration purposes. Keep in mind that the idea would also work for nonlinear functions of expectations, nested expectation. Just the properties we need are a little bit different. So in this simple case, the additional regularity assumption precisely says if we differentiate that little j, the integrand, with respect to our control or design variable u, that's that one here, then the resulting function, it should be simultaneously Lipschitz continuous with respect to both the control and our scenario, right? Which is kind of a strong assumption, but this is what you need to make this algorithm work. And in the more general setting where you do not have this clear structure here, what you would ask for is that the resulting capital J, our reduced function, which already involves the integration, it should be Lipschitz continuous. So you can easily see if this is a sufficient condition actually for this one, right? So this is what you need. This is this additional regularity. And now there's the outline for that basic CSG algorithm in combination with the gradient descent idea. What we essentially do, we need that stopping criteria. Right here, and I don't make it precise. In every iteration, at random, you draw a scenario. Let's call this xn. N is your iteration parameter. Then, for this given scenario, you solve the corresponding objective. So, in our example, for a given angle, we would compute the compliance. We compute also the gradient of this compliance with respect to your design variable. And then you somehow do not, like in the SG method, you would now simply follow this direction, and that's all. In CSG, we accumulate all the information we have from the previous iterations, choosing somehow a kind of intelligent linear combination of all these gradients. So the secret is in how to choose these weights, and this will come on the next slide. But this gives us, I wouldn't call it a descent direction, it's still a search direction. Same I can do with the objective. I choose a step length, and then I follow this step. If I have this set of convex constraints, I would still choose a projected gradient here. I do my update, and that's it. So we have somehow 3 phases. Important is that here we would only have to solve one state problem, or there are also batch methods like in SG. You can also decide for 4, 8, or 16, but never infinitely many, right? Here, that's that new key thing in CSG that you try to reuse information. But I know that there are also variants of SG who do that, but I can detail that later if you are interested, but they wouldn't work for this setting. And yeah, this I already said, it's the projection to treat constraints. So the important question now is how do we find these weights? And the motivation for choosing the weights is that we try to do something like a quadrature rule for the original function. So now, what does it mean, quadrature? You need to choose somehow the integration points, but they are chosen at random. These are the stochastic scenarios we choose. Then the question is how you choose the corresponding weights. So there are formulas for this if your function would just depend on the scenarios. But to repeat that very important thing, the function, of course, also depends on the design in every iteration. So it's a bit more than a pure quadrature rule you have to apply here. So this is the issue here. But still, you can do something similar. And that is demonstrated here. It's a complicated graph, but actually the idea is very simple. So it's a 1D example, where on the vertical axis, you see your current control or design. So we did already 10 iterations, right? Now we are in iteration 10. And here are the corresponding scenarios. So we didn't use a batch method. In every iteration, we have chosen just one scenario. That means over your iteration, you always have a pair of a choice of your design variable and a corresponding scenario. And if you remember the outline of the algorithm, for each of them, we computed a gradient for that particular choice. So in every dot here, we have a gradient. And now the whole idea, you don't even have to read all this. The whole idea is, if you can afford, you do a piecewise constant approximation of your gradient, this guy here, in that product space of scenarios and control. And then instead of integrating the original gradient, which would be along this line, you simply integrate that piecewise constant function. Okay, and integration of piecewise constant functions is rather easy. The problem is, of course, to compute this, we would call this a Voronoi tessellation of a potentially high-dimensional space. But let's accept this for a moment. These sets here, they only describe the Voronoi cells for each of the given points we have already in memory. This is xkn, such that this here, if we add this characteristic function here, if we sum over all gradients we have already in the memory and we multiply them by these characteristic functions, the effect is that we always get only one of them for each particular choice of the x. This is our given design. This is a particular choice of x. So this here, that weight is only one for one of them. So it's just a selection for a point here of the gradient, which is in some given metric, the closest one to this. Okay. So this is the key idea. But of course, that might be expensive due to these Voronoi computations. But let's continue this idea, and then I will tell you how we can do this cheap. So the idea was, okay, replace our gradient, we replace it by this piecewise constant choice, which somehow combines all the existing gradients. Now, if we integrate over, rather than integrating over this to get your full gradient, we are integrating over the model. This is what happens here. So that nabla capital J would be the integration over the original function. Now we replace the integrand by this. And of course, this is constant. It does not depend on the integration variable. So we can bring the integral inside. And now we have exactly the sum over all existing gradients times the integral of this characteristic function of that's at xkn of x mu dx. So this is nothing but the measure of the set of points in capital X, which are closest to one already computed gradient. Okay? And for instance, imagine if this would be, if you would just have an equal distribution, then these weights. So we choose these guys, we choose them exactly as our integration weights. And if you would have equal probabilities here, then these weights, they would just correspond to the length of these colored lines. But don't forget that we would not use all of them, only those for which this is non-zero, at least for one x in your set capital X. That means by this you automatically sort out gradients which are simply with respect to a metric far away and do not contribute a reasonable information anymore. Okay, so now still there is this issue of how to do these integrations here. That's the last thing I will need to explain. So how to compute these measures. And sometimes you can't because you may have only the oracle. You may have been not given your probability density, but then the simplest thing you can do, as in Monte Carlo integration, for instance, you simply replace that integral over the characteristic function by the empirical counterpart. And this is very easy. The only thing you have to do for that, for any scenario you draw in any iteration, you have to compute the distance of that pair, which is your current design and this new scenario, to all points you have in the memory. And then you just take always the smallest one, and you have your and this is the evaluation of this function. So somehow the number of such distances, it grows with the number of iteration. But calculating a distance between two vectors, it's not an expensive operation, so you can afford it. And as this is known to be from Monte Carlo integration, just the approximation of the exact measure to the empirical measure, it goes if n is the number of iterations as low as this one. This is kind of not an optimal choice. That's why we suggest still another one, and that's the one we then really use in practice. For this, I better go to this sketch here. Instead of computing these weights exactly, we simply take a priori, we choose many scenarios in that scenario space capital X. But the key is for these many scenarios, we never have to solve a state problem. They are just used for approximating the measure of these sets, the integration weights. That's why we can afford to have many of them. So for instance, in the one-dimensional case, you can imagine if I choose 10,000 points here, I have already something like an almost exact computation of the measure. And the consequences, still like with the empirical way, that in any iteration for my current design, which would be my UN here, and for any such point, for any such pair, I have to compute the distance to all the other points. So the computational complexity, it grows linearly, grows linearly with the number of iterations. Okay? And this is essentially it. I don't show you convergence proofs, but what can be shown if you do either of these choices? We have a couple of papers on this, so you can read the proof, but what you will find is that whatever your design sequence is, it does not even have to be an optimal sequence. Under reasonable assumption, the error in the function value approximation and the error in the gradient, it goes to zero, just by doing this integration on the fly. So that means your method is turning more and more from a stochastic into a deterministic method. That's what you expect. And you can, using all this, you can even show that you get, for instance, of the gradient scheme, that even for a constant step size, which is small enough, you get convergence to stationary points. And that rule here you have for the constant step size is actually the same as you find in deterministic methods. So the bound for the step size is 2 over the Lipschitz constant for your gradient. This is what you also find in 60-year-old literature about constant step size descent methods. Okay, and now this is just a visualization. So don't worry about these particles here. So here you have the function values. And what we have here is it's a one-dimensional problem. So we only have a one-dimensional design space. And what you see here is how the design evolves over the iteration. And here you see this diagram from before with all these neighbors. And what you see is what is going to happen after a couple of iterations, say 100 or 200, meaning 200 times solving your state problem. The design is already pretty much converged, and all the new points you're generating are already very close in terms of the choice of your design to the optimal design. So you more and more only do numerical integration to confirm your final optimal value. This is the typical behavior of the method. And now let's apply it and compare to some other methods. So I come finally back to my examples. This is the problem with the elasticity problem in 2D with infinitely many loads again. And the first test we do, we compute an expected compliance. Equal distribution, so all directions are of same importance. And instead of treating a volume constraint, I just do this weighted sum of the compliance and the volume constraint. Okay, and then for this, because for this, you have this unbiased estimator of your expectation, you can still use the standard Monroe-Robbins method. So then we can compare to this method. And what you see, what's going to happen. So here you have the behavior of the SG method. And this is the behavior of the new SG method. And as expected, the SG method is heavily non-monotonic because it's known, in theory, you get convergence only in expectation. And in CSG, what you see is that after a couple of iterations, the graph convergence graph, it looks already like a continuous method. So this is the change from the stochastic to the deterministic paradigm I announced before. And also you can see that already after 500 state solutions, we have approximately the same function value that SGS after 4,000. So there's a factor 8 in performance, and probably you will never go down to this with the SG method because it will always fluctuate with a certain variance around. Because you cannot prove for SG convergence with a constant step size. You have to use diminishing step sizes for this. Okay, so the designs are these two. So you see that CSG is more or less converged, SG is not. So you would have to run it for many, many more iterations. And now we can still make it test these designs. So you might see that the structure is a little bit deformed here. So these are three examples of loading scenarios. And you can see that more or less that structure produced by CSG, it's equally stiff with respect to all these directions. And this is actually what we wanted. So far the message is we can get this also by SG, but we have to wait for much longer. Now we make it more complicated. We go to chance constraint. We're still looking at exactly the same problem. We still keep equal probabilities. So we do the same, I have the same density distribution, but now we use a chance constraint, and let me express it with a failure probability. Failure probability should be below 0.025%. 0.025, which is what? 2.5%. Yeah. Failure probability below 2.5%. We are minimizing the weight and compliance, failure probability below 2.5%. And this is now already something which cannot be solved by SG. So the only chance, if you want to compare two different algorithms, is that we compare to a method which uses a priori discretization. Simply selecting a fixed number of loads out of the infinitely many. And the methods we would like to compare to is MMA, the method of moving asymptotes. I assume that everybody has heard about it, right? So this is that one method, which is the most prominent in topology optimization method. And rather than applying our plain stochastic gradient scheme, CSG, we integrate we combine this integration on the fly with the MMA method. What does it mean? Those of you who use it in practice, you know that there is this MMA subroutine. So MMA creates a sequence of problems just like SQP, but they are separable approximations. And you have a solver for this. And now all you have to do is like 2 lines of implementation. Instead of feeding the exact function value and the exact gradient into that subproblem, you feed in your current approximation with that integration weights on the fly. And that's it. Right? And then in the convergence graphs, there will be numbers. And then for both of the methods, for MMA, that means we chose a discretization with 16 loads, 33 loads. And for SMMA, which is our stochastic variant, that means we simply used batch sizes. We still work with infinitely many loads, but we solved the system for 16 or 32 right-hand sides at the time. Okay. And now this is what's going to happen. We start with MMA, and what you see here is the convergence of the volume. There's a little jump, and it's non-monotonic. This is because we use some continuations concept to get some black and white. So maybe many of you know that. More important is this here. This is now the failure probability. So 1 minus the success probability. And this is what, and we evaluate always the chance constraint with respect to all loads. So although MMA is working with a discretization of 8 loads here, we evaluate for all. And that's why there is internal, which means that what MMA can see. So it solves the chance constraint for these 8 loads. But if we evaluate for all, the failure probability rather than 0.025, it's like 85%. So that shows us 8 load cases is simply not sufficient, right? And the reason is here, if I test that design with a load which is here, I get a huge deformation, right? And this explains somehow this value up here. Okay. So now we increase, go to 16 loads, still the same picture. This is our convergence plot, still severely infeasible. We go to 32 loads, and all of a sudden, the picture in the design changes. So now, due to the resolution and the regularization for the topology we use, it's not possible anymore to choose a solution which has 32 struts. And from that point on, you know that you have sufficiently many loads, and you get a solution which is also feasible with respect to the chance constraint. Because now the other loads which you do not implicitly tell MMA about, they are satisfied automatically with the compliances. But you do not know a priori, okay? That's the point. And if we do it with SMMA, we get kind of the same function value, and we get this feasible result, even if we take only one scenario in every iteration. So for this problem with a one-dimensional scenario space, there's actually not so much advantage of SMA over MMA if you know how many scenarios you would like to take, because there's one important thing: if you solve the state equation by a direct solver and you have many right-hand sides, it doesn't generate you a lot of additional costs if you solve it for 100 right-hand sides or only for one. But still, the example demonstrates that you do not need this a priori knowledge for SMMA. And now there's one more thing I would like to say. There's also a blue curve here, because we had to introduce the smoothing for the chance constraint, which is that yellow curve. If we evaluate the unsmooth, the original chance constraint, then the failure probability would be even 0. So we choose a smoothing, which is on the conservative side. So we always a little bit better in terms of the failure probability than we have to. And in this case, you can see that we already computed a fully robust design. That's again going back to this, that we can approximate robust problems, robust solutions by high probability chance constraint. And now, also this is just a nice video. You see the evolution, so you can, with this SMMA, and you can just see the structure already very well at about 100 state solves. And then this is just more or less rounding what happens after that. Okay, so now we switch, we do the same, exactly the same with a 3D example. It's not a ball now anymore. Now we have a cube, and we move our random loads here in this rectangle at the surface. So that means our uncertainty is now parameterized by 2 variables. And another thing is, in 3D elasticity, we might now have 500,000 design variables, and we cannot use direct solvers anymore. That means if I have an extra right-hand side, I have to do a full system solve. So 8 right-hand sides means 8 times the cost for solving the state problem. And that means if you do an a priori discretization with MMR, we have to be careful. We cannot simply take 1,000 loads. So we make a decision and we take 16 loads. So we discretize that surface by 16 loads. We use MMR to solve that, and we use SMMA with infinitely many loads in this 2-dimensional space, and we compare. And this is what we get here. These are the 2 designs of SMMA and MMA, and you can already see displayed here in SMMA, it sort of almost fully covers that area where loads can appear, and MMA does not. And what you clearly see here is, of course, the discretization we chose in the design. And this you can then also see here. What this picture shows is by how much the compliance constraint, it's the relative compliance, is violated in each point of the domain. So here you have the SMMA result, and in all the blue areas, the compliance constraint is slightly violated, but this was our failure probability we prescribed. It's exactly, if you take the integral of the blue, it's just what we allow as a failure probability. And in MMA, you can see that in many more places, actually, so like in 65% of all in the load space, the constraint is violated. And if you check how much it is violated, it can be violated by a factor of 145, right? This is also demonstrated here. So if in SMMA we have a violation, it goes at most up to a factor 1.5, even if it wouldn't make a difference in the chance constraint because it's a characteristic function. But this is probably also due to the smoothing we choose. But in MMA, you have these high violations. And I mean, what does it mean? I mean, we can still look at the objective. Even for the unfeasible design, the objective in MMA is worse than in SMMA, but actually this does not make a sense because it's infeasible. That means we would need many more load cases when you discretize, but already now MMA is 16 times more expensive than SMMA. We would have to go to 100, and then you are already in the performance have a difference of 2 orders of magnitude. Okay, with that, I go back to my last example. I do it very brief because I'm already hitting my time constraint. I said it was about the optimization of that particular product of a color. I told you with this complicated diagram how from infinitely many solutions of Maxwell's equation, we can compute so-called LAB coordinates. And now, for instance, the objective can be choose a bright and at the same time a color with a high L value, which means bright, and a high A value, which means red. So this is design a red and bright color. Okay. We use some discretization. It's not finite elements in this case because this discrete dipole approximation works a little bit better for this type of Maxwell problems. We have this nested expectation with 3-dimensional scenario space distributed over 2 places. We solve the problem for 3 different initial designs. So we twice use the same topology, but once with mixed material, once with pure hematite, and once another topology, just to test to which extent our result depends on this. And we give our method a budget of 5,000 state solves. That means if we would discretize, we could afford like 15 integration points in every dimension, which is nothing. Which for one function value evaluation, it would mean a very, very coarse discretization. So we do that and we run our method. And here are the 3 graphs for the 3 different initial designs. And this is the value we are maximizing. So this is the value in this plot, at least the value of our objective function. And we end up in 3 different 3 designs, which all look pretty similar and are also similar in terms of their performance. These are, by the way, the performances in this LA function of the initial design. So the blue one was the best one, but even in that case, we significantly improve. These are the corresponding color, and this now really depends on the beamer. So this is the starting color for one of them. This is the final color. I mean, this is hematite, so you cannot change red into green, but you can make it a little bit more lighter and a little. So if we talk to the engineers of that company, we did that. We still are quite happy about such a change. So, but for a mathematician or for someone who doesn't do it on a daily basis, it looks like nothing, but it is something, right? So you can at least see it in the values. And we did in this, so this is just how the design evolves. So this is somehow astonishing that already after 1,000 iterations, 1,000 state solves, you see already the final topology, just by randomly choosing wavelengths and by randomly choosing orientations of your particle in space. And now we cannot compare actually to MMA, because comparing to MMA would mean 1,000 times at least the computation time we needed for that. And this was like, yeah, because 3D Maxwell is expensive. This was already on a reasonable computer like half a day, right? But what we can, my last slide, we can at least compare to get a feeling. We compare how much it would cost to do a single evaluation of the color using Monte Carlo. Because as you might remember, that was one of the alternatives I suggested. In every iteration, I could simply do the integration by Monte Carlo. And this is what the yellow curve is. So we fix our final, no, sorry, it's the initial design. We fix one initial design and just try to observe the convergence in Monte Carlo integration. We give the same budget for this Monte Carlo integration. This is the true value. So we use some more intelligent integration schemes. And that means one Monte Carlo integration, which would be one function value evaluation, costs more than the whole optimization. So in little bit stop, you can say with that method, you get the full optimization for the cost of one function evaluation. And this is something I think which is kind of optimal. Okay, there's some literature. Thank you for your attention.
Okay, so many thanks for a very nice and interesting talk. And now I think there's a space for questions. So if you have questions, please ask.
Okay, so I will start perhaps. So if you just have a look at that slide 97, in which you introduce the partitioning of your domain. Sorry.
Will be there soon.
Yeah.
We can take this maybe.
Yeah, this is fine. So to do this tessellation, you need to decide for a certain norm in which you will actually compute this Voronoi distribution. So
Yes.
is this something which is modeling dependent, or you just take Euclidean most of the time?
This is a very good question, because this is of course something by which you can trigger the quality of your approximation, and we have many ideas on that, but so far no clear rules how to design. But I can say that it really makes a difference, and we have seen that in this maybe a good example. So sorry for going all the way back. We have seen that actually here. So even if you can use that CHC scheme. If you fix your design, you can just choose it as an integration rule also, right? And this is what happens here, choosing different weights. So this, in this case, actually the Euclidic is good one, right? But if you take a different one, then the convergence is much lower. So this is just to show it makes a difference. And yeah, you should do it actually problem dependent, because I mean, in high dimensional integration, the only thing which can help you is that you somehow you have a chance to guess the structure of the function, because it may be super flat in one direction and so Lipschitz constants may be completely different. So if you have something like the individual Lipschitz constants, this could be a rough idea how you can choose your metric.
Like the important sampling kind of thing.
Yes. Yeah. Such ideas could help. Yeah, that's true.
Thanks. And well, just standard question. So on slide 35, you just show some results for the stochastic MMA, if I recall correctly.
Yes.
But sorry. So this you have some non-symmetry on. You just show that this is in certain sense.
Probably you mean this. This is stochastic MMA, or you mean the 3D?
No, the 35. Sorry.
35. But this was, I think, just stochastic. This was just, it's not stochastic MMA, it's stochastic gradient, but
a conventional one. So you have this non-symmetry in your design.
Yeah,
it's come from this
batch process.
Okay.
No, because you do not. But you can also control this if you wish by the batch size.
I see.
So because how would we choose the batches? Of course, we would not choose them blindly. If we use a batch size of 8, we equally distribute these batches over the circle, right? And then you have already a lot more symmetry. Yeah. But the results, they do not differ in their performance. So I know that typically one would expect that the symmetric designs, because they look nice, have the better performance, but here it's not the case. We have in our paper, we have a table of we compare all the different design, and it does not depend too much on this.
Okay, thanks. Yeah,
you're welcome.
Thanks for a cool talk.
I think there was Giovanni and also.
Yeah, mine is very short. The number of integration points you use for the volume approximation for the measure of the Voronoi cells, does that increase with the number of iterations?
No, because in all these examples, we have chosen sufficiently many. So we simply.
Yeah, so you're basically already converged.
50,000 or something. Yeah. So we mimic a little bit the analytical integration with that. But of course, this is something you need to know how many you need, right? So it is something you have to try.
That's why I was thinking that you would start with one and then you would increase the number.
Let me go to the last page. We have like 2 more integration schemes, and they are all discussed in. Sorry, now it's gone, isn't it? Okay, can you go to the last slide simply? Yeah. So you see, probably this is very new. It's a preprint on the chance constraints, but this is the theory for the method. There is 2 parts of this paper, and in that first part of the paper, we describe the different integration strategies, and there's also a dynamic one, which would take more and more points. And then we did studies where should it be linearly many, should it be quadratically many with respect to the number of iterations. And there you can find something like an optimal rule of thumb. But if you can afford to choose many from the very beginning, you eliminate that convergence of the integral of the measure from the whole convergence history. And if you don't do that, then typically this is the slowest thing. So but that's nothing we can prove, but what we observe in many of the graphs that the design, it consolidates pretty fast, and then you do only integration. So it's only your approximation of the integral, which takes still 10 times more than you did already. So if you have a chance to do it exactly, you get much better convergence.
Can you please show the finite element mesh that you used? I will follow up on the question by Jan.
I think, you mean the triangles?
Yeah.
It's just invented. It's not the mesh we used. I just wanted to show that we discussed.
I see. Okay, this one.
Yeah.
If you use a regular mesh, which would be symmetric, would that affect the result? Because the finite element mesh may introduce some initial disturbance.
Of course, but I would say in this problem, the influence of the sequence at which you take the loads is much stronger than the effect of the element mesh. So but you're right, if I take 64 loads and I keep them all the time the same, still I could get non-symmetric solutions because of the choice of the mesh. But here it's really more the sequence at which we draw the loads, because there are many solutions which have almost the same performance. There's nothing like uniqueness of the solution of the topology.